Lesson 8-4, looking at natural logarithms. An exponential function with base e written as y equals e to the x power is called the natural base exponential function. Recall that e is the irrational number with an approximation value of 2.718281. It's also referred to as Euler's number. The inverse of a natural base exponential function is a natural logarithm, which can be written as log base e of x, but it's more often abbreviated as ln x. Every point on the graph of y equals base e of x is reflected in the line y equals x, resulting in the graph of y equals natural log of x. So you'll notice that they look very similar to the common log. It's just you're using base e. Our calculators do have base e and natural log that's here in ln. And you'll notice right above it, you'll see e to the x power. You can write equivalent exponential equations by using the definition of natural logs, which would be natural log of 6 is equal to x. You can write that as log base e of 6 equaling x equaling e to the x power equaling 6. So all of those are equivalent. They mean the same thing. You can also write equivalent logarithm equations for an exponential equation with base e. So e to the x power equaling 0.5 is the same as log base e of 0.5 equaling x is the same as natural log of e equaling x. The same property that applies to logarithms with a base of e is also applied to natural logarithms. So our first example, we're going to write each exponential equation in logarithmic form, but we're going to use natural logs. So it's going to be the same way. So base e of 14 equals x. So this would be natural log of 14 equals x. Now I didn't put the e here. You can put the e there, but natural log just means base e. So this next one would be natural log of x equals 7. So you start here and end at the exponents. Next one, start with base e, which is natural log of 30 equals x. And the next one, we have base e of x equaling 8. Other examples, natural log of 4x equaling 3. And the next one is natural log of 3 equaling 4x. Question 2 says write each logarithm equation in exponential form. So we're just writing them in the other way. So again, this is going to be natural log is base e raised to the x power equals 9. Here b we have natural log of e raised to the 1.7347 will equal our x. Next we have base e raised to the 10th power is going to equal x plus 1. And letter D, we have base e of 2x equaling 11. Moving on to another example of example 2. This would be base e of 4 equals 3x. And this would be base e of 3x equaling 4. Next, example 3, we're going to write 1/3 natural log of 8 minus natural log of 3 plus natural log of 9 as a single logarithm. Now for this one, here this 1/3 goes on the 8, because if you do the reverse of the properties, that will make that natural log of 8 to the 1/3 power, which 8 to the 1/3 power is 2. So this is natural log of 2 minus natural log of 3 plus natural log of 9. So right now I have 3 logarithms here. I only need one of them. When I'm subtracting, I'm really dividing. And when I'm adding, I'm going to be multiplying those. So I'm just doing the reverse of expansion. So when I do the division, so I do 2 divided by 3. This would be natural log of 2 divided by 3. And then I have a plus, which means times 9, which simplified would make this natural log of 6. So this would be the same natural log, the same logarithm, but just written as one natural log. Next one, if I put the 1/4 above, the 1/4 root of 16 is 2. So this is natural log of 2, natural log of 10 minus, put this 2 above here, natural log of 2 squared is 4, so natural log of 4. So I multiply, so natural log of 2 times 10 divided by 4. This will give us a natural log of 5. Next, use a calculator to verify the solution. So here, we had this one as natural log of 6. So if we were to verify that with our calculator, we could just type that in exactly the way it is. So on here, clear everything. So we got 1/3 times natural log of 8 minus natural log of 3 plus natural log of 9. I forgot to put parentheses in these, end the parentheses. So 8 minus natural log of 3 plus the natural log of 9 gives us 1.791 there. And then if I did the natural log of 6, here's 1.79175, and you can see that they're the same. So you can always use your calculator to double check it, but you still need to know how to rewrite them with one natural log. Next, step this one. So here, I have natural log of 7 with this 1/3 above, so natural log of 27 to the 1/3 means 1 natural log of 3 plus natural log of 6. Write this as a one logarithm. So this would be natural log of 7/3 times 6, which would make this natural log of 14. Next, because of an exponential function with base e is the inverse of the natural log function, they can be used to eliminate each other. So base e to the natural log of x gives us x. Because remember, natural log is base e, so they undo each other, brings down the variable. Same thing here, natural log of e, they undo each other. Just like when we had 10 log base 10, they undo each other, or if I had log base 10 and this is base 10, they undo each other. Exponential equations with base e can be solved using natural log, because natural log of e is the same as natural log of e to the first, which is 1. So to solve these, we're going to solve these and then round to the nearest 10,000th place. First step is to get the logarithm by itself. So I'm going to subtract 8. And now I have negative 2 e to the x plus 3 equals negative 22. Divide by negative 2, I have e to the x plus 3 equals 11. Now if I find the natural log on this side and the natural log on here, this undoes each other, and I have x plus 3 equals the natural log of 11, and the natural log of 11 gives us 2.3979. So So that's estimated. And then we subtract 3 on both sides, and we would have x equaling approximately. So let's subtract 3 from here. And we get about negative 0.6021. So again, seeing those same steps again, if you need to see those, here we got the natural log by itself, dividing each side by -2, found the natural log of both sides to get our exponent down, and then we subtracted 3 on both sides and got our same answer. Next, solve this one around to the nearest 10,000th. So again, I'm going to divide by 4. And now I have e raised to the negative 2x power equals 15/4 is the same as, let's do 15 divided by 4, 3.75. Find the natural log of both sides. Now that brings the negative 2x here, and natural log of 3.75 is 1.3218. That's rounded to the nearest 10,000th. Divide by -2. So 1.3218 divided by -2 gives us x equaling roughly a negative 0.6609. Another one from example 4. Here we're going to divide by 6. So now I have e raised to the 0.25x plus 3 equaling 26/6. If I divide that by 2 halves, I get 13/3. Find the natural log of both sides. And now I have 0.25x plus 3 equaling roughly natural log of 13/3 is 1.4663. So that's to the nearest 10,000th. I'm going to subtract 3. So now I have minus 3. I have negative 1.5336. I'm going to, let me do that again. 1.4663 minus 3 gives us a negative 1.5337. Now it all depends on if you round it first or not. Like here, since I rounded it, 1.4663, then I have to put that in there when I subtract the 3 in there. And then I have 0.25x, divide by 0.25x. So divide by 0.25. I would now have x equaling roughly a negative 6.1348. Moving on to our next one, example 5, solve natural logarithmic equations. So we're going to solve this around to the nearest 10,000th. For this one, I want to multiply by 6. Natural log of 5x equaling 12. To undo this, I need to raise this to base e. That brings us to 5x. Raise this to base e. So I have second. So on your calculator, you hit second division for base e. Raise that to 12th power. That gives us 162,754.7914. Divide this by 5, and x is roughly 32,550.9583. Next example, solve this one. So I'm going to divide by -3. And I have natural log of x minus 6 equaling 1.5 divided by -3 gives us a negative 0.5. Raise this to base e. Then we have x minus 6 equaling base e raised to the negative 0.5 gives us 0.606 5. If I add 6 now, I now have x equaling roughly 6.6065. Moving on to example 6, applying functions with base e. Newton's law of cooling states or relates the temperature of an object over time in relation to the initial temperature of the object and the temperature of its surroundings. The temperature in degrees Fahrenheit of a bowl of soup over time is modeled by the function T of t equaling T of a plus T subscript O minus Ta times e raised to the negative 0.032t, where T subscript O is the temperature of the soap when it is taken off the heat source. T subscript A is the ambient temperature of the room, and T is the time in minutes. Find the temperature of soup that is initially 200 degrees Fahrenheit in a room that is 72 degrees Fahrenheit after 30 minutes. So we're trying to find T here, and the T subscript A, the original, or the ambient, is 72. Plus T subscript O, that's the temperature of the soup when it's taken off the heat source. So the temperature of the soup is initially 200 degrees, so that would be 200. And then the minus TA, which we said was 72. And then we're going to multiply that by E raised to the negative 0.032T. And they said that the time was 30 minutes. We're going to put 30 in for this T here. And that's going to tell us the temperature of the soup in Fahrenheit. So if I put this in my calculator the way it's written, so we have 72 plus parentheses 200 minus 72 end parentheses times base E, so second division sign raised to the parentheses negative 0.032 times 30 end parentheses. That gives us a temperature of roughly 121 we'll just run to the nearest degree, so 121 degrees Fahrenheit. Next, when Trevon was born, his grandmother deposited $10,000 into a savings account that earned 3.5% interest compounded continuously to help pay for his education. Use the continuous compounding formula, A equals PERT, to determine the balance of the account after he is 18 years old. So using the PERT formula, the initial amount is $10,000. E raised to the rate as a decimal, this is 0.035. And balance when he is 18, so this would have been for 18 years. So on our calculator, we do 10,000 times base E raised to the 0.035 times 18. And the account balance would be to the nearest cent, $18,776.11. Next part is linearizing data. You may recall that a correlation coefficient shows how well a regression line fits its data. Remember that is shown by R squared. Correlation coefficient close to +1 or -1 indicates that the regression is a strong fit to the data, which means it's pretty accurate. To determine the correlation coefficient for data points that roughly follow an exponential function, data must be linearized so that the data points are transformed to the approximate line. The process of transforming nonlinear data to appear as linear is called linearization. For data modeled by an exponential function, the data are transformed by applying a logarithmic function to the y values of the data. So consider the exponent function y equals a times e to the kt power. Take the natural log of both sides. When you do that, you now have natural log of y equals kx plus natural log of a. Remember, this is an exponent, so that goes in front. Base e is the natural log there. Because a is a constant, natural log of a is a constant. Comparing the right side of the equation to the right side of y equals mx plus b. Now you notice that the e didn't disappear. Natural log of e is 1. And then we have the natural log of a, which is 1 times natural log of a. Notice that the slope corresponds to the rate of continuous growth, your k, and the intercept corresponds to the natural log of a. So here's your slope, x term, here's your y-intercept. So thus the ordered pair x and natural log of y are modeled by a linear function. So to linearize data modeled by an exponential function, apply the logarithmic function to the output. So our first example, the table shows the estimated population of invasive tree frogs in a certain region X years since the discovery of the frogs in the region. Write an exponential model by linearizing the data and finding the linear regression equation. Then use the model to predict the tree frog population 10 years and 30 years after their discovery. So here you have the table with all our information. We're going to linearize that so we can simplify our answer. So our first step is going to be entering the numbers into our calculator to make a list or a data or a table. Okay, so I'm going to hit Stat, go to Edit, going to clear what we have in here. So we have to create a scatter plot. So I have 0, 4, 8, 12, 16, and 20. I'll move this over here. And then the other ones, we have 4.5, 4.8, 6.8, 10.4, 14.1, and 19.6. From this, we need to turn our stat plot on. So turn that on. It is already on scatter plot. Hit zoom, number 9, zoom stats. There's our equation. I'm going to hit my y equals, just going to clear everything in here. So there's my scatter plot. So from this point, so a scatter plot, which is very similar to what I have here. Now we're going to find x and natural log of y to linearize the data. So now you can see that in our table here, how do we get this 1.50? If I go back to my stats and go to Edit, we have to find the natural log of each of our y values. So if I do the natural log of 4.5 and hit enter, there's my 1.5. So I'm just going to do the natural log of my y values. Natural log of 10.4, natural log of 14.1, and the natural log of 19.6. Need to change this one. So natural log of 14.1. Now that I have that in here, now I can do the linearization part. So to do that, I hit Stat, Calculate, go to Linear Regression number 4, hit Enter, and there's our equation that we're going to use. We're going to round to the nearest thousandth when we write our equation. So to graph this one on here, so let's go to the calculator to do that one, then we'll get to our equation. So I go to y equals, hit bars, number 5 statistics, go to EQ, number 1, then hit graph. There you can see our line there. I'm going to linearize this, so if I went to stats, calculates number 4, there's our equation, 0.079, that's what they have here, x plus 1.37, so they did the nearest hundredth. You'll notice right here you have a little count on top of the y. That just means that you were linearizing the data. Okay, so the original equation is showing exponential, but to write this as a linearized equation, use that symbol there. So the correlation coefficient is close to 1. We have 0.97. So the model fits the data pretty well. Okay, now we're going to use that to, the slope of this indicates this line indicates that the population of tree frogs is growing at a continuous rate of 7.9%. How'd they get the 7.9%? Since your slope, or your k in this case, was 0.079, you multiply that by 100, that would give you 7.9%. The intercept indicates that the region has an initial population of e to the 1.37, or about 3.94 thousand tree frogs. Step 3, find the best fit model for the original equation. So use the best fit line. So again, we're using this one that they had. So you're going to substitute natural log of y in for that. And then to undo the natural log, you raise everything to the e power. So on both sides, this takes care of the natural log part, and you have y equals e times 0.079x plus 1.37. And there's our equation. We can simplify this further because I have two terms up here. I can separate them as two natural logs, and I can do this part as a number. And you have, that gives us 3.94 times e to the 0.079x. So our original data can be modeled by this formula, which we always wanted to be in y equals a times e to the kt power. Now we're going to try one ourselves here, or actually step 4. Now you're going to use that to predict the population, tree frog population. You're going to substitute x values into the equation to solve. So after 10 years, if you put 10 in for x, you'll get 8.7. So that would be, remember these are in the thousands, so there would be 8,700 tree frogs in the region. You put 30 years, you would get 42,100 tree frogs. Now let's try one ourselves. It says the life expectancy for a person in the US is n years since 1950. It's given in the table. So use the graphing calculator to analyze the data. We're going to type those in through our calculator to write a logarithmic model by linearizing the data and finding the linear regression line, and then use that model to predict the life expectancy in 2020. First, we need to grab our calculator. We're going to go to our stat, edit, clear everything that I have in here. Okay, so our L1s, we're going to go at 10, 20, 30, 40, 50, 60, 61, 62, 63, and 64. And over here, we're going to save some time by putting the natural log in here. So the natural log of 69.7, natural log of 70.8, natural log of 73.7. Let's get rid of that. Then we have the natural log of, let's go back. So here we need natural log of 73.7, natural log of 75.4, natural log of 50, so we use 76.8, natural log of 77.6, natural log of 78.7, natural log of 78.8, and natural log of 78.8, and natural log of 78.8. Now that we have them all in here, now we can use this to create our equations. So we hit stat, calculate, we need number 4. So we're going to have an equation of y equals, I'm going to put the caret symbol over here. This would be 0.0023 x, and this would be plus 4.22. So now we need to linearize this. So I would have, going to have y equals 0.0023x plus 4.22. This would be natural log, I mean. And then I exponentiate that with base e. So this would be e here and e there. And my equation would be, this would be y equals, I'm going to write this as e to the 0.0023x times e to the 4.22. And on my calculator, second e raised to the 4.22 gives us, so this would be my equation, y equals 68.03, and this would be times e to the 0.0023 and x. Now we're going to use that to predict our life expectancy. So 2020 is 70 years since 1950. So I'm going to put in right here, I'm going to put 70 in for x. If I grab my calculator here, move this over just a tad, and we will have 0, all right, clear this, so 68.03 times, and then base e raised to the parentheses 0.0023 times 70. That gives us 79.9, so that would be roughly 80 years. roughly 80 years old. And our last one, the table shows the average effectiveness of a vaccine X years after it has been administered. Write a logarithmic model by linearizing the data and finding the linear regression, then use it to find out after the effectiveness after 8 years and 25 years. So again, we need our calculator. Going to enter the data into here, so stats, edit, clear. Got 1, 2, 3, 4, 5, and 10, 15. Over here, we're going to do the natural log for this. So natural log of 75, natural log of 70, natural log of 67, natural log of 64, natural log of 62, natural log of 50, and natural log of 41. Once we have that, we're going to hit stats, calculate, number 4. Here we're going to have y with the caret symbol equals. We have a negative 0.042. I'll just do 42x plus 4.3. We'll do 4.3. We'll do 338. So 338. Now if I change, linearize this, so this would be natural log of y equaling negative 0.042x plus 4.338. Raise everything to base e, so I have y equaling, and then I'm going to raise this to base e, so that would give me raised to the 4.338. I would now have 76.55 times e to the negative 0.042x. That's going to be my equation. Now I'm going to use that to find out if I have the effectiveness after 8 years. So with 8 years, this would be roughly, we got 76.55 raised to the negative 0.042 times 8 gives us an answer of about 55. And then when we had 25 years, going to hit second enter and then just change this last number to 25. That gives us 26.78, so roughly 27. So that is our lesson on natural logs.